All right, let's find a surface area of revolution. First, it'd be a good idea to have a sketch of this. All right, so we have 4 times the sine of 2x. So the 4 is going to increase the amplitude. So we're going to go up to 4 here, go down to -4 over here. And the 2 pi is going to change the period. So instead of, sorry, the 2x is going to change the period from 2 pi to pi. So then if this is pi out here, pi over 2 is in the middle, and the sine is going to make one complete cycle from 0 to pi. And we just want this chunk here from 0 to pi over 2. And we're going to revolve that around the x-axis, and we're going to generate this kind of sine type football shape, and we want to know what the surface area of it is revolving in. All right, so let's see. That means we need to know what is dy dx. Derivative of the sine is the cosine. 2 times 4 is 8. Cosine of 2x. So that's applying the chain rule to that derivative there. Looks good. All right, next we need to set up our integral. So our surface area will be the integral from 0 to pi over 2 of 2 pi times our function for sine of 2x times the square root of 1 plus that 8 cosine of 2x squared dx. My, oh my, that's a beauty. All right, so let's see. I think I would like to do a u substitution on this. So let's try u equals 8 cosine of 2x. There's extra parentheses there. So then du is going to be 2 times 8, or 16, sine of 2x, and derivative of the cosine is the negative sine dx. And I almost have that out here. I have 2 times 4, which is 8. So I'm just missing a multiple of 2 for that. So to adjust to get that 16 right there, I'm going to multiply by a half out here and then multiply by a 2 in there. 2 times 2 is 4 times 4 is 16. And I just need a negative here and there. Negative times a negative is a positive. That's a negative in there. So now I have my du right here. All right, so with that, let's rewrite this. And I'm going to ignore the boundaries for a moment. I have a -1/2 on the outside, integral, and then this and the dx is my du, and then I have the square root of 1 plus u squared du. All right, now let's see, square root of 1 plus u squared. That is unfortunately not a trivial antiderivative. We've looked at that one before. That is the square root of 1 plus u squared times u plus the natural log of the absolute value of the square root of 1 plus u squared plus u all over 2. And I have a -1/2 times that. And technically there's a plus c, but I don't really need that here. And so then my antiderivative would be to reverse substitute back in my u here. So an antiderivative for this, if we pull out that -1/2 times 2, ought to be -1/4 times the square root of 1 plus parentheses 8 cosine of 2x squared times 8 cosine of 2x plus the natural log of the absolute value. And I'm going to put parentheses around that because some calculators need that. So then inside the absolute value, we have the square root of 1 plus parentheses 8 cosine of 2x squared plus 8 cosine of 2x in the absolute value in there. And then we're going to evaluate that from 0 to pi over 2. And then it is calculator time. And on a calculator, we ought to check both our evaluation of the antiderivative and our evaluation of the definite integral. All right, wish me luck on the calculator here. So let's create an antiderivative function first. And mine is going to be -1/4 times, and then inside there, I have my square root of 1 plus parentheses squared. In the parentheses goes 8 cosine of 2x. Close that. I don't need to see it. All right. And then outside of the square root, we're going to have a times 8 cosine of 2x. And then we need to add to that the natural log needs parentheses. In the parentheses is absolute value. In the absolute value is the square root of 1 plus parentheses squared. Inside there, 8 cosine of 2x. Just be really careful with your parentheses. And then inside the absolute value, but outside the square root, we have a plus 8 cosine of 2x. Wow, that is an amazing antiderivative. Okay, so then we want to know what is a, I'm always curious, what is a of 0? Does it really zero out? It doesn't. Okay, didn't think it did here. So we want a pi over 2 minus 0. So it looks like the surface area is 33. And we'll double check that in a couple of ways. I'm going to check my integral from 0 to pi over 2 of parentheses 2 pi times my original function, which was 4 times the sine of 2x. And then that is times the square root of 1 plus the square of the derivative of that function. Derivative of 4 sine is cosine, so that's 8 cosine of 2x. And I already got the square there, so that should be the antiderivative. Close the, sorry, that should be the integrand. Close the integrand, tell it what variable we have, and I got a different answer. Oh boy. Okay, what did I do wrong here? 2 pi times 4 sine of 2x, that looks good. And then 1 plus 8 cosine of 2x, that looks good compared to notes. Okay, my antiderivative must be the problem. Interesting. So I must have mistyped something there. Let's double check that formula, which I'd used earlier. Okay, antiderivative of 1 plus ax squared, which is kind of like my u, but my a is 1. That looks right. Okay. Where did I go wrong? Substitution must have a problem. Let's double check my substitution here. So my claim, let's see, we didn't quite have, we have in green here, a 2 times 4 is an, oh, I forgot my pi. There it is. So if I go sneak in here a pi, let's put it outside. All right, don't forget your constants. Wow, that was fun. Other way to check this would be to approximate it with some other function. And thinking about that for a minute in my graph. Over there. Here so you could kind of approximate this with an ellipse. It's not quite an ellipse because it's not, ellipse is flatter, rounder on the edge over here. I'm gonna have to look up the surface formula for an ellipse. Not bad. Anyway, I think we're pretty good. We have an antiderivative that seems to match the integrand. We have a surface area.